Hey everyone, thanks for staying with us for the last session of the day. So I'm Akshay Shah.
I'm Zahra from Oracle.
So we're both from the Oracle database team, and we're going to talk about how we are integrating SPDK into the Oracle RDBMS product. So this is just the agenda. We actually presented here last year. We highlighted some of the challenges and the work we're doing. Some of the challenges that we faced in the past 12 months, that list has increased, and we've come up with other additional enhancements and solutions as well. We'll move on to the architecture after covering the challenges, and then go on to some of the very specific features that we've built on top of SPDK, which is the Oracle ENV and the Oracle Dispatcher. And then we'll end a little bit with the support model and some future-looking stuff. So last year we spoke a lot about performance and how SPDK in general helps improve the performance of the database. I/O performance is very important to the Oracle database in general, and that's where we see SPDK being a really significant help. That said, there are a few challenges that are involved when we're trying to use SPDK with our product and our infrastructure. Our goal is to use SPDK and these really high-performance NVMe SSDs as a consolidation platform for deploying various databases. Now, when we talk about deploying different databases, these could be completely separate software instances that need isolation and so on from each other. They could very well be different customers running those databases in Oracle's cloud infrastructure. So what we need is we need the ability to sort of control a lot of the memory management that happens. And if we are using the DPDK model, that was one of the challenges that we faced and we had to solve. Additionally, when you're deploying something in the cloud and running separate tenants as separate databases, you want to make sure they're isolated and they're secure from each other. I think the 2 points sort of blend into each other at that point. When we're using the DPDK primary secondary model, a lot of the memory allocations are not isolated. So if you're deploying two databases, they may both be sort of allocating memory from similar segments in the primary. And some of it could be shared, there could be malicious users and so on. So security was another big aspect for us where we wanted to segregate all of those allocations. The third thing is recoverability. What we wanted is if there is a database that for some reason is causing some memory leaks or causing buffer overflows or data corruptions, how can we isolate the memory data structures between the different databases so the problem is sort of isolated to one instance and doesn't bring down the entire node and the entire fleet of databases running on that system. The fourth point is restartability. Let's say in case of some software bug, you're running like an NVMF target on the system that's serving the various databases that are deployed on that machine. And for some reason, there's a bug which causes some sort of a hang or a deadlock in the target, and it's not able to respond to requests coming in from the databases. We want the ability to detect some of these kinds of scenarios from our manageability software and potentially restart and recover to keep the database instances running. And lastly, scalability. Scalability was something that we covered a little bit last year as well. So RDMA NICs have limitations in terms of the memory registration and limited sizes of the caches that are available for storing those mappings. So we'll sort of go over how we are overcoming that limitation. Also, NVMe devices have a limited number of hardware queues, and Oracle databases are deployed with thousands of processes within a single database. So it could be tens of thousands of processes across a few databases. So we would easily exhaust the hardware queue, so we've come up with an innovative solution for that as well. So let's quickly look at what the architecture looks like. So this is a picture of an Oracle real application cluster. We've shown a couple of VMs here. Each VM is running 2 databases. So these are clustered databases. So we have instance 1 running on VM 1 and instance 2 for the same database DB1 running on the second VM, and similarly for the second database, which is called DB2 over here. If you look at the bottom below the NVMF target, it says we have created an ASM disk group with 2 fail groups. We'll go into a little more detail of what this is. But at a very high level, ASM is automatic storage management. You can think of it as a simple volume manager that Oracle owns. What we are doing over here is we're trying to access the NVMe SSDs that are local to the node directly from the database. And then the ones that are remote, we are accessing those through the target. The table on the right sort of enumerates the various aspects of the software features that we've built. The ones in red are what Oracle has built. The device management aspect is really device management, memory management, RDMA key management, and so on. Zahra will be going into that in a couple of slides. And then we'll sort of switch back to how we handle local and remote IOs with the Oracle NVM dispatcher and the NVM library. So just to summarize, SPDK, basically I already highlighted sort of the performance aspect. We've seen that SPDK gives us with these really leverages these high performance SSDs with low latency, and we can get millions of IOPS at that low latency. I think other talks have already highlighted the advantages of using a user space model as opposed to going through the Linux kernel. And at our scale, it makes a big difference of avoiding going through the kernel and the overhead of the interrupts. We sort of highlighted the other challenges. So we can now securely deploy multiple databases with this architecture. Since it's a 2-node cluster, it can actually go to multiple nodes. With NVMe over Fabrics and Oracle ASM, we can now have a highly available and a fault-tolerant system where a single device failure should not cause any sort of, there might be a brownout and some noticeable performance impact, but the system will still keep running. And lastly, all of this we are hoping to have RDMA capability. Oracle has deployed a lot of database solutions with RDMA capability. We are hoping to sort of leverage the reduced CPU utilization and the lower latency that we can see with those technologies as well. And we'll go into more detail on those as well. So at this point, I'll hand it over to Zahra.
So before I go through that how we implemented OraEnv, I want to emphasize again that why we implemented OraEnv. So as Akshay mentioned, Akshay, can I have, hey, Akshay, can I have control? So as Akshay mentioned that in Oracle there are 1,000 processes. And Oracle, I mean, engineers, they work several years to come up with the idea to, manage resource, to kind of control this resource management efficiently in the Oracle to have optimal and scalable execution in the customer workload. So we really, really wanted to have Oracle resource manager management in the SPDK. So that was the main reason that we wanted to have Oracle environment rather than, I don't know, like DBDK environment that we have it now. So because in current SPDK, DBDK, it's, takes care of most of the part of this resource management in the SPDK. So the first step was to kind of getting rid of DBDK. So for that, we implemented, we worked with Intel team and we implemented some different patches. The first one was that just a simple, line in the SPDK lib make file just to link SPDK with user environment rather than, for example, using DBTK environment within SPDK. And the second one was that to add additional field in the SPDK ENV options, like ENV context. With ENV context, we could integrate or we could have Oracle resource management within SPDK. But so what does this OraEnv include? It takes care of memory management like memory allocation, deallocation, physical addresses of the memories. It also provides remote key and local keys for the remote memory accesses. It also takes care of all of the PCIe scanning, enumeration, or LCore initialization. We also include enhancement for RDMA transfer for targets that I will explain for each of them in the next few slides. But for the memory management, in Oracle database, KGH interface takes care of memory management. I mean that in database we have 3 different regions in the memory. First one is PGA, which is kind of the area that is private per processes. And the other one is SGA, which is going to be shared between all of the processes. So in SGA, all of the processes have the same access to that area. And the other thing that is cool, and we wanted to have this in the SPDK, is MGA, which is manageable global area, which means that we can manage the area to be accessible with some specific processes, not all of them. And spaces in kind of heaps, they're composed of continuous chunks. So whenever a user it wants memory from heap, he will just specify flag, like if I want from PGA, MGA, or SGA, and then KGH will provide a pointer from data specified heap to user. But the thing is that in SPDK, or because DBTK takes care of memory management for SPDK, the memories are either private or they are shared. So there isn't any kind of manageable, shared memory in SPDK. So for actually specifying, which region we want to allocate memory for SPDK, we defined 2 new flags. All of these patches have been merged, so you can find it on SPDK 19 or even SPDK 18.1. So these 2 flags, the first one shows, specify that, for example, I want memory from DMA, which is going to be, direct memory access. This memory, this buffer is going to be allocated from MGA area. And if the flag is specified by share, so it means that it's going to be shared between all of the processes. So it's going to be allocated from huge page, and it's going to have the same access to all of the processes. So we applied this patch, so we added this flag as one of the arguments in SPDK malloc or SPDK zmalloc call. So then we can specify, for example, for the controller pages in the SPDK, we wanted it to be allocated from SGA, or we wanted actually to be, we wanted it to be shared between all of the processes. So we passed a share flag for controller pages. But for example, for the data path, we wanted it to be from manageable global area. So for that, we pass DMA as a flag there. This picture shows, it's kind of simple, and it shows the design of the OraEnv. In OraEnv, we also have primary and the secondary processes, but it's kind of a bit different than the one that we have now in the SPDK. So it's the same. Primary will initialize some steps, and the secondary, when it's started executing, it first attaches to those, for example, memories, and then it's continuous execution. But the thing is that here in the OraEnv, primary is some specified process that's going to be run for all of the time. Then the other processes like target, perf, or Oracle database are going to run as a secondary. In this picture, I'm showing two database instances. There are two processes within each database. And so as you can see that there is SGA memory region that is shared between all of the processes within one instance. So that all of the processes have the same access to the memory of SGA. And MGA are kind of, we can manage to be shared between some processes, like in the first database, client 1 and client 2, they have their own MGA memory pool, but in the second database, MGA is shared between these two processes. For all of the memories that is going to be allocated using that share flag, all of the secondaries, the secondary is going to ask for the primary to allocate that memory. But for the other memories, secondary can allocate it from its own MGA memory pool. So with this design, we kind of solve the problem that Akshay was mentioning in the first slides, the security problem. So because in SPDK, there isn't any access policy for the secondaries. So secondaries can have the same read and write access to the memory that is shared between them, which it causes security problem in the database. But with MGA concept, we can kind of solve that problem. The other thing is that because it's in the Oracle data environment, so we also took advantage of the other features in the database, like recoverability. So that means we are kind of preventing memory leakage or data loss when one of the process, I don't know, it's just shut down abnormally. And the other feature that it's also in the progress is a restartability for both primary and target processes, because we don't want to actually, so as I said before, that this primary process is going to be run forever. And so when the primary exit abnormally, or if it's shut down, so we didn't want the secondaries to to force them to also stop. So for that, we added this feature. So when a primary exit, so we can spawn another process, and then it can attach to all of the pages, and so the current secondaries, they just continue their IOs without any problems, and if new secondary that comes up, it will just wait for the primary to be restarted and then continue its execution. So the other feature that we added as we included in that ENV context in the SPDK apps was that to pass the enhancement that we have in the database for RDMA transfer. The reason is that registering entire memory region in each process, it's not scalable. So the solution that Oracle comes up years ago was that using a shared protection domain. So what does it mean? It means that the first process will allocate and register memory using this shared PD. And the other process, when it comes, it just attach or map to that allocated memory, and it will use the same shared PD. This is, all of these enhancements are included in that MGA region. So, which means that it will, so here we will use just one PD across all of the Oracle processes in one, within a database instance. And so it will kind of, help us to scale more. And this PD is going to be valid as long as one process is attached to that. So that was very cool. So we also could add that into SPDK, I mean, using Oracle. But for adding this, we applied some other patches that mostly are included in the nvme.h. So it includes that RDMA hooks. So we added these two callbacks. So because we wanted to pass or PD into the SPDK, so we defined this get IBB PD within that hook, and also we wanted SPDK to use or provided our keys for accessing to the remote memory. So we defined this get get our key call in the hooks. So after initializing hook, so we could pass Oracle PD by just calling get IBB PD within NVMe RDMA or NVMF RDMA, and also we could use or provided our keys within those files as well. So I'm showing you result. So this result is kind of our first result that we got. They're in progress. There are lots of enhancements that we have proposed, and we are implementing them. But in this stage, I mean, for the first step, our main focus was to actually keep the performance the same as DBDK, not to losing performance, and then making it better, which we also could achieve that. So the first row, actually, I mean, I'm comparing performance between OraEnv and DBDK on perf application in the SPDK. The first row shows perf that is using PCIe. The second, which in this example, OraEnv is a bit, on the average, is a bit better than DBDK, but it's kind of 1%. And in the second row, it shows the average performance of perf with target but loopback, which means that perf and target are just in one node, and the performance was almost the same. And the last row shows perf with target but remotely. And in that case, DBDK was kind of a bit faster than OraEnv, like 2%. But overall, I mean that from our experience, the performance was kind of the same, but we could have more features in the SPDK, like the one that I told, that solving the security problem, having recoverability, having restartability, this kind of cool stuff. So for that, we wanted to, so now we have targets that is fully enterprise secured. It's highly resilient and recoverable. It's it has HA highly available. And the other thing that we also, I mean, working on it, it's not finished yet, but it's kind of in a progress. We wanted to actually add some SQL comments for targets, which is kind of very cool because, for example, we wanted to get namespaces from targets, or analyzing memory consumption and or resource utilization on target. We can also get the number of clients that is connected to that target by just running this one command in SQL. Yeah, Akshay will talk about Oracle Dispatcher.
Thanks, Zahra. So now that we've looked at what the Oracle environment abstraction layer gives us, let's look at the dispatcher. And this is going to focus more on performance and how we do IOs from the database in the SPDK model. So this is sort of the summary of the architecture slide that I showed you earlier. So we're using ASM. So ASM here is discovering all of these NVMe devices. We use the word local and remote across this slide presentation. So local for us are devices that are accessible over PCIe, and remote are the ones that we are accessing using NVMe over fabrics. So ASM allows us to create fail groups. So we can basically mirror IOs. Each write can go one to a local device and one to a remote device. And that sort of gives us the HA. So fail group is basically if a node goes down, it takes a fail group down with it. At that point, you are potentially accessing remote devices to get to your data. We've also configured, ASM has a feature where you can configure a preferred fail group. So in all of our experiments, we have configured the preferred fail group to be the local group. So reads in a system where you always have data on a local device, the reads can always go over PCIe and have a lower latency as compared to going over the network to a remote node. Obviously, in configurations where you have 5 nodes but 3 mirrors, the data may not always be available locally. So the latency that you see for those kinds of applications and those configurations would be a little bit different. Then just to highlight sort of where the dispatcher fits in. So as Zahra mentioned, we have various memory regions. So there is the SGA/MGA and the PGA. So this year, because of the lack of time, we didn't go a lot into Oracle's architecture. So Oracle is a multi-process model. And last year's slides have more details on that, so you can go refer to it. But basically, the dispatcher slaves are separate processes. So any memory that's in SGA is mapped into the dispatcher's address space. So it can access that memory region and use the PCIe namespace to do the I/O directly. PGA I/Os are private to the process memory address space. So those ones are sent over the NVMe over fabric namespace. And it may either go over loopback to a local device or go to the remote node, depending on the situation. And then remote I/Os, which obviously if we are mirroring writes, we would have remote writes happening. So those are submitted directly to the SPDK via the Oracle NVM library. The Oracle NVM library is just effectively an abstraction built on top of SPDK. The dispatcher is where we've changed how the I/O architecture looks like. It's basically a proxy. And we can now sort of go into what the dispatcher looks like. So it's basically an I/O proxy. As I mentioned earlier, we have thousands of processes in a single database instance. So we run out of hardware queues relatively quickly. So we've basically implemented a dispatcher, which is a small set of slaves. And all the clients are sending a message to the dispatcher to get their I/O serviced via the dispatcher. Each dispatcher slave is running on its own dedicated core. It has a bunch of request queues. The clients are basically queuing the I/Os to the request queue, which is implemented as a lock-free ring. I'll go into that in a couple of slides. Dispatcher also reports the completion back to a separate completion queue. Each client has its own completion queue. And it can poll the completion queue to check if the I/O request has been completed or not. And as Zahra mentioned earlier, our OraEnv primary is basically the only primary that's running on the environment. It's managing the devices that we've discovered on that system. The NVMF target is running as a secondary for that OraEnv primary, the same way dispatchers are also running as a secondary to that OraEnv primary. So what does the client look like? So clients, just to load balance between the various dispatchers, a client, when it spawns, is bound to a particular dispatcher slave and an associated request queue that's being managed by that dispatcher slave. We don't currently have it, but in future we could do load balancing where clients can move between dispatcher slaves if the load is sort of uneven. With the lock-free implementation, the clients that are on the same request queue need to be running on different cores. So we do that using by specifying the core masks for those clients. Obviously, if the request queues are different, for some clients, they can be running on the same core. The completion queue, as I already mentioned, is specific to each client. So dispatcher is the one that's putting the I/Os in that completion queue, and the client is polling for those I/O completion. from that queue. So just a slightly more drill down into how these queues are implemented. So we can see here that we have two clients. They're both trying to submit an I/O into, in this case, they're sharing the request queue. So they're both submitting an I/O into that request queue, which is being managed by a particular dispatcher slave. The dispatcher slave is the one that's invoking the SPDK APIs to submit I/Os to PCIe devices local to that system. And then once the I/Os are completed, it obviously polls the devices for the I/O completion. Once the I/Os are completed, it will place the completions back into the client's completion queue. And each client could either be asynchronously doing other stuff, but if it comes and it wants to wait for an I/O, it's actually polling for the I/O completion in that code path. Okay, so let's now look at some performance numbers. So we basically ran some tests. So this was, the setup was a 3-node Oracle real application cluster setup. It was based on the Oracle X6 platform. So it has these Xeon E5-2630 processors. So this is the older generation. So this generation had the Samsung NVMe SSDs. So there were 6 devices that we were using on each node. So we had a total of 18 devices across the 3 nodes. We had created the ASM disk groups. This was created as a high redundancy disk group, which basically means for each block you have 3 copies. So each write would be replicated to the 2 remote nodes as well, in addition to writing to the local device. We were using a calibration workload. So in the database world, whenever you're running transaction processing workloads, a lot of the queries come in, they use some index, and you end up eventually reading a single block. 8 kilobytes is sort of the most commonly used. It's the default, and it's the most commonly used database block size. So I would say 99% of transaction processing workloads, the workload would be 8 kilobyte random I/O. And then the read to write ratio can vary based on the application. So we noticed over here, running that random read calibration workload, with 4 dispatcher slaves, we were able to see 1.7 million random read IOPS. We scaled up the dispatcher slaves to see if the performance goes up, and the performance did go up. We are seeing 2.25 million IOPS, which is kind of close to what the datasheet number for those SSDs is. In this case, I should mention that the reads were all going just to the local devices. So everything was over PCIe in this experiment. We've identified some bottlenecks, and we're sort of working towards alleviating those. So even with a smaller number of dispatcher slaves, we can reach the max IOPS. We hope to run some more experiments with the next generation X7 and X8 hardware, which has the newer generation Intel SSDs, where we are expecting, the datasheet numbers are higher, so we're expecting to see better performance with those. So lastly, I wanted to sort of talk about the database support model and how SPDK sort of fits into our ecosystem. And we envision a few sort of challenges, and we wanted to sort of present those, and we'll work with the community to see how we can come up with solutions for those. So what does the model look like today? So Oracle traditionally has been deployed on-premise in our customers' data centers. Even today, with all the move to cloud, a large percentage of our deployment is still in on-prem data centers. Our releases are around for a long time. Oracle long-term releases are traditionally around for 5 to 7 years, sometimes even a little bit longer than that. The real application cluster that I mentioned is managed by a piece of software which is called the grid infrastructure. The whole goal of grid infrastructure is to manage the cluster, make sure there are events that are generated when nodes go up and down and so on, and sort of just maintain everything at a cluster level. The GI software usually is responsible for supporting older database releases. So we traditionally have a database release that comes out annually. The GI software in the 5 to 7 year time frame, if you keep refreshing the GI software to the latest release, it's supposed to support older software releases up to 5 to 7 years. Obviously, some of the features might not be compatible, but functionally, everything that was supported in an older release should keep working with a newer GI. And at least the way we are targeting, ASM is already part of the grid infrastructure, and the OraEnv that we have built, we're sort of hoping that fits into that grid infrastructure, and I'll explain why it fits into that model in my next slide. And our customers, obviously, the reason for supporting older releases is because customers are running a mix of newer and older databases. Some of their more mission critical stuff, which is well tested, could be running on an older database release, and some of the newer stuff might be dev or even QA. They could be testing out some newer releases and deploying additional features on top of that. So how does SPDK sort of fit into this ecosystem? So with the latest 19.1.1 SPDK release, there's been a lot of work done around packaging. So that's sort of where we are driving towards. We're trying to figure out how the packaging will fit in with our Oracle use case, and what more needs to be done along those lines. So the first thing is we now have similar to DPDK, there's a long-term supported release for SPDK, so that's a good start. Critical fixes, security fixes, and so on that are identified in general by everyone in the community are automatically being backported into those critical releases. There could still be some more process around identification of those bugs, communication of some of those critical bugs to everyone in the community, but that effort has sort of started, so we can evolve it further and improve it. The other part that I mentioned previously, that we want our OraEnv to be part of grid infrastructure. So that's where sort of this API and ABI stability comes in. So let's say SPDK 19.10, the last release for 2019, has some new features that we want to use for the Oracle database. And Oracle could potentially have a database release coming out around that time. So we could integrate that, but the older Oracle release that has already gone out, it might not be something that's backportable to an older Oracle release. So now what we would need is our OraEnv, which is part of the grid infrastructure, is running at the latest release. That has to talk with an Oracle SPDK initiator in some sense that's running an older release and a newer release, and one of them's not supporting the feature, the other one's supporting the feature. So I think that's where a lot of the API and ABI stability and how new features for SPDK are developed over time becomes important. And the other concern that we have is our time frame is 5 to 7 years. Obviously, as you start adding new and new features, the code line diverges significantly. So even if there is an SPDK release that's, let's say, 2015, that we want to backport some critical fix to today, the fix you merge to master and the fix that needs to be backported, that those two code lines are so different that there's no way you can really backport. It's like saying you fix something in master, now you have to re-implement that fix for an older release. So those are some of the challenges that we see going forward. And I believe there is a plan to come up with a proposal and discuss how some of these problems can be addressed in a developer meetup that will happen a few months down the line. Okay, so that pretty much covers what we had. So before we move on to questions, I was told that there's going to be a raffle, so everyone stick around. If you ask us questions, you probably get 2 more credits towards the raffle. So we welcome questions from everyone.
I apologize, this is kind of a dumb question. You have 3 nodes in a fail group, so when you do writes, it goes to the 3 nodes. But your test was using reads, so what happens to the usage of the 3 nodes in that scenario?
Right. So the test, what we were trying to showcase in the test framework was so the reason we are doing the reads locally is because the latency is lower than doing it from a remote node. So each block that we have for that 3-node cluster, each block is present on all 3 nodes. So this was an I/O simulation workload, but let's say you're running an actual application. An application connects to a database using a service, and the service can load balance you, and you may connect to any of the 3 nodes. Once you connect to those nodes, you would do the read locally to the PCI device on that node. So every read would happen local, and you would get the best latency in that model. So I haven't gone into details on if you do writes, how does the cache coherency work and all of that. There's a lot of collateral already available because it's not specific to this deployment. A lot of that collateral is already available about how Oracle database achieves that when you're making updates and changing data. So we didn't sort of cover that part, but for the reads, we are going local because that gives us the lowest latency. So in this specific case, yes, but the process is running on that node, and the process is accessing the device locally.
What entity is doing the load balancing?
So the load balancing in a real, so this was a I/O simulation. So in the simulation, what we do is the workload figures out how many cores you have on each machine, and it spawns that many slaves. So it's basically equal load across all of those, and the slaves look at the files that the database has created. So it creates a logical volume. Let's say you have 100 files. It'll create one logical volume spanning all those files and just pick random offsets and do those IOs.
So then when you doubled the number of dispatcher slaves, you ran out of cores? Is that why it doesn't double the IOPS?
No, so when we doubled the number of dispatchers, we hit the data sheet number for the IOPS for those NVMe devices. That's why it didn't double. Okay. But what we were trying to show was we probably have some optimizations that we can do in our software that with 4 cores, we can hopefully get to the max IOPS with 4 dispatcher slaves without having to double it up to 8.
With your dispatcher, you have multiple clients bearing down on a single common work ring. That's a finite sized work ring. How is it divided up amongst the clients?
Right. So clients basically, so each dispatcher has a set of request queues that are implemented as the work ring, and clients map to a particular, so when a client is spawned, it's mapped based on the load balancer, it's mapped to a particular dispatcher and a request queue that is being, each dispatcher has a set of request queues, and it's mapped to a request queue that's being managed by that dispatcher. If the request, when it tries to queue an IO, submit an IO to the dispatcher, if the request queue is busy, it sort of circles around to the next one to see if there's a free slot available and submits it to that one.
Okay, thank you.
So I have two questions about the long-term support and what SPDK components are Oracle interested in? SPDK NVMe driver and environment, or do you have any interest in other components? And the second question is, if I understand correctly, you may utilize kernel driver before using SPDK. So have you done any effort to make easy to have long-term support for Linux kernel?
Okay, so let me restate the questions to make sure I understood. So the first question was, what other SPDK components are we interested in using? Okay, so far we're using sort of the NVMe driver, PCIe as well as for remote devices. There are other components. So BDEV is something we may look into. In last year's slides, we presented some stuff about quality of service. There's already some rate limit capabilities that are available that we are interested in. When you're deploying sort of multiple databases in our model, if we want to provide quality of service guarantees to those databases, we could potentially use BDEVs and enforce those rate limits, and then that can sort of be our target as opposed to using the regular target. So yeah, there are those other kinds of features built on top of. Right now we're using sort of the vanilla blocks, the basic building blocks, and then DPDK was something that we had to replace with our ENV. But all the value adds that have been built on top of it, these are the few we've looked at. We've also sort of looked into how we can do IO tagging for providing hints and so on. So those are some of the other areas we're interested in. The second question, if I understood correctly, was have we tested with the kernel, and do we have any numbers around that?
If you don't use SPDK, you will use kernel?
The kernel driver, right? Yeah, so we don't have performance numbers for that comparison.
My question is, you may be struggling to keep up with SPDK's update. So do you have any struggle to keep up with kernel's API change or something?
Right. So let me try to. So the reason we haven't tested with the kernel is we are expecting scalability issues with that, with the number of interrupts and so on. So that's part of the reason we want to use SPDK. And Intel had already documented numbers where they showed SPDK gives you more IOPS per core as compared to the kernel driver. And sorry, what was the last part of your question?
So kernel's API is more stable?
Yes, so the API part, so what we are hoping to see is, right now a lot of the SPDK software is in flux because a lot of rapid development is happening and so on. So we expect some of this to stabilize over the years. What we are hoping to see is if there is a well-defined process, we don't necessarily, our newer database releases can adopt the new features, but we just want the ability to easily maintain our older database releases which were built using previous versions of SPDK. So as long as we have a pathway to doing that in a maintainable manner, what we worry about is, let's say a new release comes out and we refresh our GI, let's say to SPDK 20, and we find out that there are bugs that we are now seeing with our code that was using SPDK 19. Those are the issues that we worry about because we have to support our databases for a much longer period of time.
Thank you so much, Mike. Thank you.
I have one. On your first answer to the previous question, you mentioned interested in SPDK's NVMe driver, both for PCIe and Fabrics. When Oracle is using a virtual machine, you could perhaps get a virtual NVMe controller that would just look like a PCI device and it would probably just work. But you could very well get other types of storage controllers that SPDK already has drivers for today. For example, Verdeo is SCSI. So does your implementation today work with that, or is there any issues or just testing?
So yeah, so we haven't tested with that. So far we've been focused on PCIe and NVMe over Fabrics. But again, we're using standard SPDK APIs. So as long as we can instrument our code to discover those devices. So I mentioned the ASM part. So there's some code there that's discovering these namespaces and so on to create our disk groups. As long as that can be done, we should be able to issue IOs over any device that SPDK supports.
So did you have any tests over Vertigo SCSI yet?
We haven't run any tests apart from these ones.
Okay, thank you.
All right, thank you.